here are some of the profiling tools, and these are the product-specific profiling tools, as I told you. We have the kernel profiler for Windows CE, Microsoft Source Profiler that it's not longer implemented because it was for Visual Studio 6.0. We have the SQL Server Profiler, which is now outdated and is going to be replaced with something else. It is replaced already. Then we have the COR Profiler, which is a small tool written to showcase the COR profiling API. We have this another NP.NET profiler that again tries to utilize the COR profiling API. And we have the Visual Studio Profiler, which is the most complex profiler by Microsoft written today. And we have other tools. It's not just this. We have a huge list of profilers by different vendors. These are all just managed profilers. The principle is more or less the same with every single one. The only difference is that, for example, this one is just native. I think it has some managed code also, but it's primarily for native code, including the CPU counters. It processes CPU counters here. The difference between the rest is more or less the way how they process the sampled data and the instrumented data. Because at the end you get, with a lot of data, more or less all tools get the same data, but the tricky point here is how to process that data, how to visualize it to the user, and how to analyze it to give him a recommendation what to do next. So every single profiler has its own good and bad sides. It's hard to wrap them up right now, but what about Visual Studio? This is actually a really funny Stack Overflow question that I found some time ago. And in the conversation down below, there are some guys just saying, oh, in Visual Studio 8 I haven't seen a profiler. And then the next one, Visual Studio has a profiler. So there was also surprised that Visual Studio has a profiler. The reason for that is that the profiler used to be Visual Studio Ultimate feature. That is the most expensive license. But the real good news today is that it goes down to the professional version, the profiler. So it's a really complicated tool that now you can use in Visual Studio 2012. It's really powerful as long as you know how to use it. The Visual Studio Profiler has its own, is bundled in the IDE, but also has a standalone version. And it works with sampling and instrumentation. And it also do code and memory profiling. So you can find the exact location and exactly how much of the memory has been taken. And of course, the speed, that is also important. So, I already talked about instrumentation, but let's just wrap it up again. So, instrumentation works by injecting probes at compile time. That is important. So, if you want to do instrumentation for a website, then you have to recompile the complete website and eventually publish it again to the production server, right? Or the test server. So, it's not very easy to do. It's probably best to use it during development when you implement some feature and you run it through the instrumenting profiler to find out how fast it is, just for a specific feature. You get a detailed execution plan, and with the downside that it's working only for the instrumented code, so you cannot see what is happening outside of the world, outside of your code in the operating system. And because of the fact that it injects these probes, it's actually slow. So if you run it on a website that it's under heavy load, this won't help you that much. I mean, it will slow you down a lot. So what to do? Instrumenting is really good to find out when you have scoped the problem to a specific method or a specific class, and instrument just that one. So you get the problems, the detailed execution into that class. Then we have the sampling. Sampling measures at specific intervals, and the intervals can be, and by default, it is a million CPU cycles. So every single million CPU cycles, it gets a sample from your application, right? It can be also done by page faults, by system calls, and by CPU counters. So more or less, sampling is based on CPU sampling, on CPU execution. It also has the capability to extract a call stack. So every single sample comes with a complete call stack that goes next to the kernel. So yeah, and as I told, it covers all the code, so you can see what is happening with other methods, not only your. It's really good for running in production. It takes about 10% utilization of the total CPU, but it's good to keep it running for a little longer period of time. How does it work? The tricky point that you have to remember with Visual Studio Profiler is that there is only one instance that can be instantiated at a single point of time. And that instance is controlled by this environmental variable, and you turn it on and off with this variable by setting it to 0 and 1, and that's the GUID of the profiler. So remember that huge list of different third-party profilers that I showed you just a few slides ago? Every single profiler has a separate GUID, so you should make sure that sometimes when you install other profilers, Visual Studio Profiler can break and stop working. That's because another GUID for the profiler has been set, for example. All the profilers are based on the COR Profiler API that implements these two interfaces. And the first interface, it's allows you to call to COR to call you back, so you can load your infrastructure, and then you get called on every single sample or for every single instrumented piece of code. The runtime itself, you have when you start profiling an application, you basically have the Visual Studio IDE, or this tool, VSPerf command, that orchestrates the whole process. They are responsible for making all parts work together. Then you have this process that collects all the data, and the data is collected from the process itself, but it's collected from the kernel by using a system driver that's called VSPerf driver. And it tracks the kernel time, how much time is spent into the kernel and how much time is spent into your application, so you know what is the kernel utilization of your code. And it also tracks the CPU counter, so it can give you information, can give the profiler information when the next sampling sample data should be taken. When you get all the data done, you use the VSPerf report file to generate a report, or you can also compare two different files and see what's the difference between the two performance reports, profiler reports. And one important feature here with the VSPerf report is to pack symbols into the file itself. I'll talk about it in a second. So the output of the whole profiler process is a VSP file. It's a single Visual Studio Profiler file, and it's important to remember when you do a production profiling on a production system and you have a VSP file that is generated, before you move it to your development machine in order to analyze it, you need to pack the symbols inside, because symbols are specific for that particular machine, and you need to run vsperf report /pack symbols in order to get the symbols embedded into the VSP file. Also, you have an API that you can control the data collection. That it's a little more advanced technique. Okay, so now let me show you how to work with the Visual Studio Profiler. Let me just see how we're doing with time. Okay, we have good enough time. Any questions? Okay, so I have this application. That's the second example that you'll find over there. That draws Mandelbrot diagram. It's basically doing this. Okay, so it's a very intensive computation operation, and we won't go that much into details of the implementation here, but let's start and run the profiler now. First, again, remember, we need release, and we need to make sure Visual Studio host file is disabled. Alright, then let's try the instrumenting profiler. Here in the profiler, we can say a new performance session, or initially we can just use the launch performance wizard until we get used to it. Launching the performance wizard, we have the CPU sampling and the instrumentation profiler. We'll talk about memory in a while, and resource contention. But right now we have CPU sampling and instrumentation. So let's instrument it now and see what is happening here. We say that we want to instrument the project Troll Mandel. And okay, just launch it then automatically, and that's it. Visual Studio does all the infrastructure for us to instrument the application. It compiles it, now analyzes the downloads all the PDBs that are needed, and analyze the data and visualize it. So what is happening here in the output window is first instrumented the exe file with the tool for instrumentation. Then it copied the file to the output folder, and then it started the profiling itself and created this VSP file here. That's the output. So the VSP file is then opened in here. Actually, if you have a VSP file sitting somewhere, like this. You cannot open it with double click. You have to drag and drop it into Visual Studio. That's one way. Or another way, just to open it with File, Open, File, right? Just to know. So let's see what's inside. Now we can open it here. And that's our instrumentation report. We see the CPU usage. And remember, that's instrumentation, so we only see about our application execution. We don't see anything about the rest of the system. So this CPU usage is about our application. Okay. We have the wall clock time, and that is important to know. What does the wall clock time mean? By wall clock, the Americans usually mean that putting the clock on the wall, that is the total time spent, just by the initial moment of start and the end moment of start. So this doesn't show you your time. That's, for example, you used only 1 second of the whole process of the processor, but the overall application took 10 seconds, right? So it won't show you this 1 second that you only used, but it will show you the full 10 seconds that you used from the start to the end. So in here we can see that Visual Studio, what Visual Studio does really interesting is giving you a hot path. Right now this application it's really small, but in a large application, when you have a lot of methods, then finding the hottest path that takes the most of the time, it's really useful to quick identification. So we have the hot path, and then we have another drill down of the work by different methods and by their time here. So let's talk a little bit about inclusive and exclusive parameters in here. These are important for you to know. So as you can see, and this is actually pretty good to see in the instrumentation mode, because in sampling you probably won't see it that much clear. In the instrumentation, it all starts with drawMandel.exe, right? That's the process. So the whole process took 100%. And that's including all the functions that the process has executed. So, but at the end of the day, the process itself took 0. It's not the process that took the time, it's the functions inside it, right? So then we have the next one, app.main. App.main took like 66% of the time, but it's the functions inside that took most of the time. The function itself, main, took very small time. So it's not the app main who caused the problem, but it's the functions that app main called, right? And then we have inclusive time of 33% of drawMandel method, and we can see, okay, here this method actually caused 15% impact, but there are other 15% that is spent in the functions that it called, right? So that's the difference. Inclusive is the time spent in this method and its child. It's in its children, the functions that it called. And exclusive, that is that explicit time that this method has taken. And this is just a summary information about the report. So in here we have different options to compare reports, to save it, export it. Remember again, you need to set the symbol path. And again, if you didn't do it until now, you have to do it. Okay, so that's the summary. what we have here, we have different views. We have a call tree, which gives you the full call stack like this. And if we expand it a little bit here, we'll see the same, more or less the same information. But this time, what we saw on the first screen was just the hot path. It was scaled down to some methods. But right now, we can see from here that Joel Mandel actually called system.mat.square-root. And square root took this 13% exclusive time. So looking at the exclusive and inclusive time, they're more or less equal. In this situation, they're absolutely equal. It means that this function didn't call anyone else. The whole time is spent in that function, right? So we can also understand from here that there are additional 33 minus 15% time that is spent in this function, draw Mandel, because we're missing what it is here. Okay, so let's try to find out, and maybe I can show function details from here, and that's really powerful here. We have a visualized graphic of what is happening. We can see that there are the draw Mandel, the function body of draw Mandel spends like 15%, but there are additional time spent on square root and different
Is it only time spent in this operation of square root, or the entire run where square root is used?
That's the entire run.
So if someone else called square root, I would also see this here in this.
No. It's coming from Joel Mandel. Yeah. So you can have it, the one that you're looking for. Probably you can see it here in functions. Then you can have the square root, and you can see that it's called 4,000 times, 4 million times, and and it took that amount of time, but.
Because we have only one.
Yeah, because we have only one. Yeah, exactly. So function details we were at. Okay. So in here we see that.
But if you look several times, it calls square root several times inside this function, do you get the aggregate result here?
It's actually looped already.
That's what I meant.
Okay, so because we don't have symbols for square root, it just doesn't show results, doesn't show us the source code here. But that's really powerful, and again, if you don't have the symbol set up, if your symbols are not indexed with the source files location, as it has it here, then you won't be able to get this information. Okay, so now we can find that Joel Mandel spent some time itself to do some work, and that it counts for 15%. But still, it's kind of hard right now to find out which line exactly took a lot of time, right? We still know that this function, but we're not aware exactly where in this function we have the performance issue. Okay. So just let me see how to proceed now. So there are a few optimizations that we can do here. So one is immediately we saw that the square root is taking a lot of the calculations. And that's actually a true example. It's not artificially made. It's a true example from a code project that someone implemented this function. But if you look at the mathematical expression of it, you will find out that this should be equal square root of this one should be equal to, if we remove the square root, it should be equal to this, isn't it? So we remove the square root and just power them to, let's see what happens. Yeah, we got the same result.
This is a way to change the code.
It's what?
This is a correct way to change the code to find where your function lost the time.
No, it's not the correct way. I'm saying that we saw that the square root is taking a lot of our time, right?
But the circle is
So
changing code you can see.
I'm showing that we have a problem with square root, and we're seeing that it's just redundancy here that someone implemented. So I'm removing the square root, so we don't need it to see the performance optimization afterwards, right? So we have it here. Let's run another instrumenting session. Actually, the first time when you create the profiler, when you start it, here in the Performance Explorer, you have the configuration for the profiler. So in here, you can start the profiling again, or you have a more detailed view of how to configure the settings of the wizard.